Thank you, everybody, for joining us today for our latest in our sponsored webinar series. My name is Bill Griffin, Professional Development Manager at Informs. Today's webinar is presented by AMPL Optimization, and it's entitled Teaching, Learning, and Applying Optimization, AMPL's Intuitive Modeling Meets the Python Ecosystem. Your presenters are Bob Forer, President, AMPL Optimization, and Philippe Brandau, Director of Development at AMPL Optimization. Bob is Professor Emeritus of Industrial Engineering and Management Science at Northwestern University and President of AMPL Optimization. He's written extensively on optimization modeling and computation and has served as an area editor for leading journals in the area. His work has been recognized by our Informs Impact Prize and his election to be a Fellow of Informs. Philippe is Director of Development at AMPL, where he oversees and/or leads most software development projects. He has a PhD in computer science with a thesis on integer programming models for cutting and packaging problems, which is currently being used in the industry worldwide. Bob and Philippe will present. We will reserve time after for 15 minutes for Q&A. Feel free to put questions in the Q&A in Zoom, and we will get to them in the order in which they were asked. Without further ado, I'll turn it over to Bob and Philippe. Take it away.
Thanks, everyone. So let me start out by just outlining what we're going to do today. And I will do the first part. And this is on the intuitive modeling that we've tried to add to AMPL and the reasons for it. So I'll start out with some general background and motivation just to make it clear to everybody what it is we think of as optimization and what we mean when we say you want to write optimization models more like you think about them. The main part is describing how we rewrote our interfaces to various solvers so that you could write optimization models a lot more like you think about them and make it easier for people to both teach and learn optimization as well as to apply it. And I'll finish with a few other aspects of AMPL that have been enhanced recently. And what you'll see in a number of these examples is that Python figures fairly strongly. So the second part of the presentation, which Philippe will give, is about AMPL's ties to the Python ecosystem and how you can take, in fact, in teaching a Python-first approach to presenting AMPL. For example, analytics programs that have standardized on Python can fit AMPL right in there very naturally. And Philippe will also present a number of enhancements. We've continually improved the AMPL Python interface to make it more powerful and useful. I'm going to start out with 3 slides about optimization. And just let me note that we have various links on a bunch of slides here and also at the end for getting more information. And you can also anytime just write to us at this general address, and then your query will be forwarded to someone who can help you. Okay, so the first 3 slides to set the stage. The way I think of optimization in general is you're given some need to make a lot of interrelated decisions of various kinds, like you see here. And you want to consistently make highly desirable choices of these decisions and by applying ideas for mathematical optimization. And that's ways of describing problems we call models and ways of solving problems that we call algorithms. And you can see this is somewhat more general than the old-fashioned textbook approach that says optimization is finding the optimal solution. Somewhat broader than that. Okay? And now, the kind of optimization that I'm talking about today that is really widely used is what's called model-based optimization. And the idea is that you start with a general description of some class of problems. It could be the class of power transmission problems or some kind of class of portfolio optimization problems or some kind of general production or distribution problem. But it's a general description. And then when you combine that with data for a particular scenario, then you get an optimization problem instance that you can solve. In general, there's going to be a lot of these scenarios over time that you use with this model once you get it working. And then once you've got these together and you have a problem instance, you send it to a solver. And the solver is the one that actually applies the algorithms and computes the results. And returns you some highly desirable decision, which hopefully is close to optimal in some sense. And then you can deploy the results. So the key thing here is that these model and data and solvers are independent. Writing the model does not involve putting in the data. The data is a separate thing from the model. So your model is general and can work with all sorts of data scenarios. And then the model and data implementation is independent of whatever solver you use. So you can use all sorts of solvers, pick the one that's best for your situation. And you don't write a solver specifically for an electric transmission problem or a portfolio problem. You write a general solver that can work with all sorts of models and data. Now, the particular kind of model-based optimization that has proved to be really widely applicable is what I call algebraic model-based optimization. And that's where you define it sort of in a mathematical way. You have various sets and parameters that describe the data of your problem. Then you define some decision variables and an objective, which is some function of the variables that's the one you want to make as big or small as possible, and a variety of constraints that the variables must satisfy in order for the solution to be useful. So as a result, model-based optimization software tends to be of two kinds. And one on the user side is software for working with the models and data to develop and implement applications. And the other software on the solver side is to work with the data structures and such to actually optimize them, solve problems. And AMPL fits into this class of problems. So this is what I'll be talking about, is the modeling side here. So then let me tell you, our whole idea with AMPL was that you would write these models more or less like the mathematical formulation looked. What I want to do is show just how that works, but then show how really the mathematical formulations, the traditional ones, were not broad enough, and we had to extend AMPL to encompass everything that people wanted to say. Our whole theme here is writing optimization models like you think about them. The idea is you design this modeling language that looks like mathematical model notation, and then you build a system, which is like the AMPL system for working with the models and also the data and the solvers. So here's an example. I've been just saying everything very general here. Here's an example that I'll use throughout. And it's a multi-product network flow problem. You want to ship products efficiently to meet demands. And it looks like this. You have various locations. You have various shipment routes. Those are called nodes and arcs. You have supplies at some plants here, and you have demands here at some places where you sell this product or warehouse it. And you have capacities on these arcs and shipping costs as well. And so the idea is how much to ship of each product on each arc so that the shipping costs are kept low and you respect the capacities and the supplies and demands are in balance. So the traditional mathematical way of writing that is you've got three sets, a set of products, a set of nodes, and arcs, which are just pairs of nodes, an origin and a destination. And you have three kinds of data. Like, for example, the capacity on the arc from I to J for every arc is given by Uij. And similarly for these other two. And this is typical of the whole model formulation, that things are indexed over sets. The variables are the same way. For every product and for every arc, from I to J, there's an amount of commodity P to be shipped on the arc XPIJ. Then given those variables and those data, we can write the total cost, which is the objective, which is just summing up all the costs times the amount shipped. And then there are two kinds of constraints. And one just says that total shipments on an arc are less than or equal to capacity. And this one is showing the balance at every product at every node. Shipments in plus net supply equals shipments out. So we designed AMP. This is a linear model and the just simple linear expressions. And we designed AMPL to represent that. So the whole thing can be written the same way in AMPL like this. And everything here corresponds directly to something I showed in the mathematical description. So you see the three sets, and you see the three kinds of data that are indexed over various combinations of sets. You see the one kind of variables that are indexed over products and arcs. And then you see here the objective function, which is the sum over products and arcs of the cost times the amount shipped, and the two kinds of constraints. And if here I've written the flow balance constraint, and it's for all products and nodes, just like here. And here I have a sum over arcs of XPIJ, and here I have the same thing, except instead of X, I've called it flow to make it more obvious. And I add on this, which is the net supply, and it equals this flow out here. So it really translates directly from the math is the idea. You don't have to just figure out too much. That's how we did it originally. But what we found was that there's a lot more to mathematical models than just linear expressions or even nonlinear expressions, that there's all sorts of logic and special kinds of functions that are used and so forth. And that if you want to write things the way you think about them, you have to be able to express those things in your model as well. And so our particular motivation was that we had actually put into AMPL at one point a bunch of logical and sort of almost linear, but not really linear expressions. And our solver interfaces had limited support for those. And basically, you could write them, but if you wanted to actually do anything with them, you had to convert them to something else. And I'll show an example of that right now. And then I'll show some more examples are more real and difficult just to show what we were up against. So, and this is all made possible by a new AMPL software interface library that allows many more types of expressions to be used. And it automatically converts them for each solver to the form the solver wants. So some extensions are natively supported by the solvers. Some have to be linearized. So I'll show some examples now. So here's the same problem, but now we imagine that there's some fixed costs of whether, if you use an ARC, you have some fixed costs you incur. Shipments can't be too small. Not too many ARCs can be used. And let's see how you would express those. So what about fixed costs? Well, a reasonable way to think about that is, well, you sum over all ARCs, not only the shipment costs, but if there exists a product that has positive flow, then the ARC is used. So you sum in the fixed costs. Now, if you wanted to use that using our old solver interface, you had to turn that into something linear. And to do that, you had to define some binary variables. So there's this binary variable trick. You define these 0, 1 variables and some fixed costs, and you add this thing where you add the fixed cost times the 0, 1 variables. And if the variable is 1, that means that you actually use that ARC and the fixed cost gets added in. If the variable is 0, you don't use that ARC. So here's another one. Shipments can't be too small. So you could say that what we'd like to say is that the total flow along an ARC is either equal to 0 or it's between the minimum shipment amount and the capacity. Straightforward enough. But the way people have traditionally done that is to say, well, you can do that with the 0, 1 variables. If there's a trick for doing that, so that when the variable is 0, you ship nothing. And when the variable is 1, you ship more than min ship and less than or equal to capacity. And this is actually, so you have to, if you're teaching a course, you have to teach how to use these 0, 1 variables like this and how to do these tricks. If you're implementing something, you have to, an application, you have to be sure you get the trick right. And it's actually more complicated than it looks, because even if the min ship is 0, you still need these constraints in order to make the fixed cost trick work. And if you don't have explicit capacities, you have to find some capacities. There's a number of fine points. And a third part is we said you can't use too many ARCs. And one way you can say that in AMPL is that at most max ARCs of all the ARCs have the sum of flows being positive. If you need to linearize that in order to get the solver to solve it, then you have to rewrite it like this. You sum up all the used variables and the sum should be not more than max ARCs. Now, if you're someone who's familiar with mixed integer programming formulations, you might say, well, this is all pretty obvious to me. You can learn this trick to where it's really pretty clear and it looks pretty neat and compact and so forth. But in reality, this is just a simple example. And linearization is seldom that simple. That's what I want to show is just some more practical things that people have shown us. And these aren't even the most complicated ones. For example, a student said, well, I just want to say that if this variable equals this variable, then this constraint should also hold. Okay, so this constraint holding implies this constraint. Another one, here somebody has all sorts of cases in their objective function. Another one is here, this is for an assignment model that I did that says that one of two conditions has to hold. It's actually somewhat complicated, but it corresponds exactly to what the client said they wanted. They wanted either no people assigned or at least 2 people of a certain kind assigned. Once you get into more realistic things, the linearization is not so clear. Just as an example, let me show what happened to this person here. So someone actually wrote in and said, yes, I want to show this. And I wrote it in AMPL, and the syntax was there to write it in AMPL. When they did it, they got this horrible error message from Cplex. Said, oh, I can't do that. I can't deal with this at all. I had to even explain what it meant. And so I wrote back and said, oh, yes, you have to do it in a different way that Cplex will accept. What you have to do is define some binary variables, lots of them, and break it into 2 parts. And this part here, actually, Cplex has, because there's only a binary variable on the left, Cplex will accept this one. It actually knows how to translate that, but it doesn't know about this one. So this first one, I have to break that into 2 more constraints that are linear that it'll accept. So I've taken what the student wrote that was clear to the student and straightforward, and I've converted into a bunch more variables and 3 constraints of various kinds. And this is and of course, I'll write this down now, but what if the conditions change? What if the next part of the assignment says to do something different? Well, then you have to figure this out all over again, because probably the linearization is different. There's another one where Gurobi complained about there were 3 binary variables, 3 0 1 variables multiplied together. What am I going to do? Gurobi just throws it out. It's not quadratic. I don't know what to do about it. So I had to write back and say, well, Gurobi is smart enough to know quadratics, but not cubics. So you have to define some more 0, 1 variables to equal the product of these and put that into your constraint. So I had to do all this stuff. You see, it's not even, you have to read it for a while just to figure out what's going on. And then I said, well, you could also just linearize the whole thing with this. So originally the student just had 3 variables multiplying each other. It was clear what it was supposed to mean. If they're all 1, the result should be 1. And it's been converted into this really complicated thing. And this is what we try to avoid by allowing people to write the product of 3 0, 1 variables in AMPL directly. Here's another Gurobi one. This is from Gurobi's Python interface. It actually has all the power of all these extensions to Gurobi. So there's a max function that you can actually use in this Gurobi Python interface. The user wrote this, which they thought was pretty straightforward application of that, and it gave them this horrible error message, unsupported operand type. So the Gurobi support had to write them a big explanation. And no, you can't do this, it says, and you can't do this, but if you write all this, then it'll work. And what we wanted was that they should be able to write it like this, just like an AMPL. In AMPL, the syntax is right there in AMPL, and the ideas in AMPL, you should be able to write that. And it should just figure out what to do with it. It should convert it, should do all these conversions automatic, because this is really clearly what you wanted to do. It's easier for students to understand what they're doing and to learn modeling. And it's easier to check that you got the right thing. In this phase, let me just conclude by saying that I have a list here of all the things we've added, and you can see a number of implications here, if then else's, things like OR, various logical operators, this min and max, also absolute value and more general piecewise linear functions, various kinds of counting things, comparisons, more general comparisons, not just greater than or equal to and less than or equal to, and an all different operator when you have a bunch of variables and they all have to take different values, complementarity constraints, various nonlinear things that can be handled either approximately or exactly by solvers. And you saw one where we used multiplication twice to get like a cubic function, and we want to be able to deal with that without you having to reformulate it. And membership in arbitrary sets, also high order polynomials and various kinds of conic constraints. I actually have a slide for every one of these. There's not time in this presentation to show it, but I'll add it to the slides that we post. So just to finish up here, I want to talk about 2 other aspects of AMPL have been enhanced to make it easier to teach, learn, and apply. First, the modeling environment. The traditional modeling environment in AMPL was sort of command line. You basically told it some files to read, and you told it to solve, and then you asked it to display the results. And there are slightly fancier ways to do that, where you can have some sort of application with a bunch of windows, but this is still basically the command line of AMPL. This can be great for doing something simple, fast, but we always encourage instructors to make it clear to students that if you actually have to do an application, it's hard to do it if you just stay in the AMPL environment, because the rest of your enterprise has lots of other programs that you're going to need to connect with. And to make AMPL easy to connect with other programs, we developed APIs in half a dozen programming languages that let you connect from any application in those languages to use AMPL directly from them. One of those is Python, and the Python one we've developed especially well, and that's what Philippe will be talking about. So there's something called AMPL that runs in notebooks, that we have a whole collaboratory of examples that people can use online without any special registration. So you're going to see in a moment a lot more about this. We encourage people who are teaching it to incorporate this sort of thing somewhat into their curriculum so that students understand how this fits into the world of computing. The other thing I'm going to mention briefly is data interfaces. There's a native plain text data interface, but there are also various other kinds of data sources that are supported, all sorts of Python data. So I'll show you just 2 things because I have like 2 minutes left. One of them is that we've always had some sort of a spreadsheet interface, but if you wanted to say like the capacities here in your spreadsheet, you had to have every pair of from city and to city listed out with the capacity. And then you could write something like this that basically, you can see there are 5 tables here, and it had a description of every table and table in the spreadsheet related to the table and the data in AMPL, and then you would just read them all. And the only thing that I want to point out here is that we made it so that if you added an extra 2D to these, it would read 2-dimensional tables. And this is a much more natural way to show shipments from and to. And now you can have these kinds of tables, and they're supported just along with the old 1-dimensional tables. And then I'll conclude by saying that Similarly, the Python API tries to deal with the data the way you want to express it. This Philippe will explain this Google Colab kind of screen in a moment. And I just want to say that you can put AMPL models into these Python notebooks. And then when you put the data can be like Python lists or dictionaries and so forth, and also pandas data frames. And so all these kinds of data are also accessible from AMPL. With that Python example, I'd like to turn things over to Philippe, who will talk about AMPL meets Python.
Thank you all for being here. In the second part, it is going to be mostly about live demos showing the AMPL being used in practice from Python, and also to show resources that we now have available. This is the outline. I'm going to start with a very quick introduction to AMPLpy. Then I'm going to show Colab. After that, I'm going to explain how this is working, how is AMPL available from Python, AMPL and all solvers available from Python. Then I'm going to show how to quickly develop optimization applications and to deploy them. One simple example, just using Streamlit, and also how to really deploy large-scale optimization applications. And the main thing that you need to keep from this is that the code that you write, even on Colab, can go all the way to the large-scale deployment with minimal changes if you follow the right practices. Let's get started. So what do you really need to know to use AMPLpy? You need to know the basics from Python. You need to know lists, dictionaries, and so on. Also, you need to go for any reasonable size application, you need to know how to do data manipulation using pandas data frames, because it is the most common tool out there. There are also a few others that we will be connecting to, but right now, pandas is the main one. And you also need to know how to model in AMPL. And the first part was a lot about how to write the AMPL models. In this second part, I'm going to focus more about how we then connect the AMPL models to Python to send data in and out. And here I'm mentioning that you can even ask ChatGPT to write your models, because we also do the same. Let's start with a small example. This is our model laboratory where we have many notebooks. And here we have a special notebook that was not written by us. It was last year around Christmas, and we just wanted to write a Christmas model. And we had no idea what to model. So I asked ChatGPT to do that for me. And it wrote this model. And I was extra lazy that day. So I also asked, okay, can you write the Majax code for Colab? And it did that. And that's this part here. And here is the model. The model is a very simple gift assignment problem. There is a set of people. There is a set of gifts, a parameter cost with cost of each gift. Then a parameter happiness, which is the amount of happiness that each person gets from receiving each gift. There is a budget for all gifts that you are going to buy. The assignment variable, that is going to be 1 if you assign the gift. So maximize total happiness, subject to the budget. And you want 1 gift per person. So a very simple model. And in terms of data, so set of people, it can be just a Python list, and you can assign it just like this. The set of gifts, it can be, again, just a Python list. The parameter cost can be just a dictionary, is just 1 parameter. It will also be a pandas data frame if you want it, and you will assign just the same way. The budget is a scalar, so you just assign the value of the budget that you have. For the happiness, you have more possibilities, because in this case, you have 2 indices. You might have your data in this format in pandas. So you have essentially a 2D table. For each pair, you have a value. Or you can have it stacked like this. So for each pair is an index, and you have a value. But it does not matter which way you have it. You just assign it, and it will take care of understanding how to load the data. So at this point, we have the model loaded. So this cell here took care of loading the model. Here we took care of loading the data. Now we just need to pick a solver, and we solve. In here, I'm retrieving the solution. In this case, I'm using an AMPL expression to filter just the non-zero assignment variables, so that we get just the pairs in which x, p, g is 1, and then we just print the solution. But then you might want to change your budget, switch also your solver. And in this case, I want to retrieve solve. And in this case, I want to retrieve the solution as a pandas data frame, just to show a different way to retrieve data. And so this is a pandas data frame that goes into solution. And I want to filter from that pandas data frame. I want to filter just the ones with value 1. So the ones that we are assigning. And I'm displaying it here. So this is the pandas data frame filter. And here you just code again to go through this pandas data frame and just to display again the solution. And just one last one. So the CVC, another solver, we can change the budget again. We could also change other parameters. We change the solver, we solve again. And in this case, we retrieve the variable X as a dictionary. And in this case, I'm retrieving all for every index. So I need here to filter and just print the pairs for which the value is 1. And that's it. So in terms of input and output, you just use the native data types in both directions. And your model, you express the model in AMPL, which is very close to the mathematical notation that you see here. Okay, so this was to introduce a little of AMPL. Now, another example, but this one is more to highlight one particular detail about the reformulations provided by the new solver interfaces. In this case, I'm going to show the n queens problem. In this problem, you have n queens that you want to place on a chessboard, on an n by n chessboard, so that no pair of queens can attack each other. For that, one way to do that is using the all different constraint from constraint programming. But we want to use a regular solver, not a constraint programming solver. And our interfaces are going to take care of that for us. In here, we have variable row that is going to indicate for each row in which column are we going to place the queen. This first constraint ensures that every queen is on a different column. The second constraint ensures that we don't have queens in the same diagonal like this. And this last constraint, the same diagonal like this. And let's go to the notebook. Let's run this notebook. Just to see what you need to do to use it on Colab, you need to install AMPL. Then from AMPL, you can import AMPL Notebook, which is a utility function that allows you to pick a set of modules to install. And modules are often just solvers, all the solvers that you want to use. But there are also other plugins that you can install this way. The license, since it's an open source solver, you can use the default license on Colab. Otherwise, you can use the Community Edition and also AMPL for courses. And at this point, the notebook and the machine is ready. We load the model. We set the parameter n, which is the number of queens. We pick the solver i's. We set some options. We solve, we retrieve the solution, and we display. And we can just change and see that it is quite fast. And i's is an open source solver, linear solver. There is nothing in it for constraint programming, but the reformulations that we do for these constraints, they are quite good. So in this case, we don't do any kind of reformulations. In here, there are lots of big M's, but we try to do them in the most efficient way so that even a solver that is not prepared for this is still able to tackle these problems. And of course, when you do this with a powerful solver, then you reach another level in terms of performance. Just another example. So far, we are showing some toys, something bigger now. . Network design. And in here, you have a big collection of problems with over 50 examples. And you can also contribute with examples to be added to Colab. In here, I'm not going to enter into much detail. I'm just going to explain in high level what is happening here. Essentially, you have a bunch of nodes, and you want to build a network connecting these nodes. But to build each arc, it has a cost, and they have also capacity limits. And you want to decide the set of arcs that you need to build so that your network is prepared to survive in case you lose one node. So one node disappears, you need to still have enough arcs to keep connecting every other node with enough capacity to satisfy the demands. This is the model in mathematical notation. And one big advantage of AMPL is that you express your model in a way that is very similar to the mathematical notation. And then you just load the data. Just like before, you just assign it. In this case, I'm using Groovy because this is another problem and it takes longer to solve. And here we have a solution. Here we can see in the default state in terms of the amounts that go through each arc in order to satisfy the demands, assuming that we did not lose any node. But in Python, one thing that we can do is to then use these plotting libraries to plot, for instance, what happens in each scenario. So every time a node disappears, what will happen, for instance, without node 6. So if node 6 goes down, the flow here needs to be 0, but we still satisfy the flows, the inflows for every single node out there. And this is going. And one thing that also happens often in practice is, so you have everything ready, but then someone decides to change the rules. So it occurs to someone that having a network prepared to survive to the loss of one node is not enough. So you need to adjust your model. But since we have a very clean separation and between model and data, you just need to look into your model again. You make the changes, the appropriate changes directly in mathematical notation or go directly to AMPL. And you load the data exactly as before, you solve, and you are now solving a different problem without changing anything else. Now let's get back here. And just this one, I'm not going to show the notebook, but is to show that we update this quite often. And for instance, Groovy 11 was released not long ago. And we already have a notebook where we are showing, for instance, with IP-opt, we can get stuck in a local optimum. And now with Groovy 11, we can also solve a very nonlinear problem, something that a few years ago would not be something that you would expect to solve with Groovy. In this case, the problem is just minimize 1 plus this nonlinear expression. And now you can just use Groovy to optimize problems like this, and way more complicated than this, using nonlinear functions in them. So now I'm going to talk just a little about how this is working. So how did we get AMPL and all these solvers working on Colab? One thing we did, we repackaged every single solver as a Python package, and we made them available for all these platforms. So Windows, Linux, and some weird architectures like this. But even architectures like this, they are quite important. For instance, NASA and some big companies have clusters just running on machines with these architectures. And also regular day-to-day machine like macOS supporting Apple Silicon. Not for every solver. We still don't support every single solver for Apple Silicon because they are still also not available. But for the ones that are available, we are already supporting them natively. To install, you install AMPL, you run this command where you pick the modules that you want to install. So this is similar to what you do on Colab, but to run locally. And then you activate a license. It can be a community edition license, or you can be, for instance, an AMPL for courses or a commercial license. And then you just import AMPL from AMPLpy, instantiate the AMPL session, and you start using. On Collab, like I showed before, you install AMPLpy, and then you have this utility function that is going to do the same as the commands from the previous slide. If you want to try it really quickly, you can go to try.ampl.com and you get access to a Collab notebook with just a few cells with this part so that you can just run it and see how it feels. Now, in terms of a Python first approach to learn and model with AMPL. So if you are already in the Python environment, you might want to just add some optimization component to it. And an easy way to learn that might be to just look through examples. And we have Collab with a substantial set of examples. But in Collab, there is one issue that in terms of organization, since this is a result of contributions from a lot of people, there is no organization like in a book. So to fix that, we now have this book here that includes the problems in a more organized fashion. So mathematical optimization, linear optimization, mixed integer optimization, network, convex, conic optimization. You can see mosaic and Grow being used. Optimization on the uncertainty, robust optimization, stochastic, two-stage stochastic. So a large variety of applications. This notebook was not initially made for AMPL. So these are the authors of this book. But since the book already included the models in mathematical notation, it was really easy for us to just rewrite. And we adapted the book to AMPL so that people can now use it for teaching. Just to show from here, I'm going to show just one small example. Yeah, this one here. This is related to the first part of the presentation about the reformulations. So for instance, in scheduling, one thing that often happens in scheduling, you have something like this. You need that either a job for every pair of jobs, they need to be before each other, they cannot be overlapping. So you might need to express a constraint that looks like this. And if you need to linearize it yourself, you might have to think it a little, but in AMPL, you can now just write it. So finish job A before you start job B, or finish job B before you start job A. And in order to do an exclusive OR and not finish job A before you start job B, and finish job B and start job A. Since this is an XOR, we also have the XOR function. So you could just say finish job A before job B, XOR finish job B before you start job A. So it will be another way, and it will also be automatically reformulated exactly in the same way. This is just to show the power of this reformulation. And we are again just solving this using an open source solver that has nothing special for constraint programming and to deal with logical constraints. So now, in terms of deploying optimization applications quickly. One very easy way to do that is using Streamlit. You can go to ampl.com/streamlit and you get access to a set of examples that we made available here. So nquins. So in the beginning, I showed the notebook on Collab for nquins. And in there, I was changing the number of queens. And here I'm changing it again in the same way. And every time I change it, you see the solution also change. So let's look at the source code for this. To do a Streamlit app and to use AMPL and solvers in there, you need a requirements file where you put the modules that you need. This first line here is to indicate our Python package index where we have the modules available. Here is the list of modules that we use in the examples. And this is AMPLpy, and this is Streamlit. Now, the entire app is just this file here. And when you see in the beginning, import Streamlit as ST, because I'm going to use it in this program, and import also AMPL from AMPL. This block here, in triple quotes, is typically just a comment in your Python script. It renders like this, marked up. And this is copy paste from the notebook that I showed in the beginning. This notebook here, it was copied directly here. And here, so after that block, we instantiate the AMPL object, we evaluate the model so that it is loaded. We pick the solver, set some options, and then we have this slider here. And the slider corresponds to this slider that you see here. Every time you touch the slider, it is just like you have put a different value here and you rerun the script. And it will just update automatically. So if you have a Python script that you run locally, or you have something that is in a notebook, you can very quickly turn it into an interactive application like this. And then there is some code to display the solution. And here, again, a markdown block with what we show at the end. So in terms of more realistic examples, we have, for instance, for people interested in data science, we have an example showing how to do logistic regression using exponential cones. For people that want to see the math behind these functions that students typically use to just classify. So if you want to really understand how to solve the optimization problem that is going to find, to optimize the parameters that will find this curve that will split the points in order for you to do the classification, this is a good example to look at. And in here, we use two models. One of them is just a convex optimization model that we need to solve using, for instance, IPOpt. And here is how we use it from AMPL. We load the model, load the data, and so on. And here is a conic model. And this one is in particular just to show how to do conic programming with Mosaic. But the most interesting part is what you can do with Streamlit, that is interactive applications. Here there is a lot about data sets, about what happens when you play with these parameters and so on. But the interesting part is at the end, where we can play with parameters ourselves and with different models. In here, we have two data sets. The first data set is a data set about ships. If they are yellow, if the points are yellow, so we have two labels. And if the ships are in these points here, they are marked as yellow, they are good. Otherwise, they are bad, so they are broken. And we want to find a curve that will capture all the good ones, all the ones whose parameters will mean that they are in good shape. This is on the training set, and this is what happens when we use the same curve to classify on the testing set. And here we have the accuracy on both training and testing. And here we can play around with a parameter for regularization. This is to prevent overfitting. In this case, you cannot notice a big difference. Let me switch to the big data set. So on the big data set, you can see what happens when you increase the parameter. So an high value means that you are going to overfit less. You are introducing a bigger amount of regularization. A low parameter, you are going to fit quite tightly. And this, you see what happens on the training set. So all the points are really inside. And this is on the testing set. We also have a finance example here. But this will take a while to go through. And in case there are questions, I can come back to this at the end. But essentially, the good thing is that Streamlit is really easy to create these interactive apps, and you can quickly move from something that you have locally or on Colab to something that you have on Streamlit. And also, other than having something running on Streamlit, you want to then do a large scale deployment, because if you are doing something that you want to then deploy, you are likely going to deploy that into Docker containers. But Docker containers is exactly what is already running under Colab, running under Streamlit, and so on. So for a generic application where you have Docker containers, you just pick any Docker image with Python, you install AMPL, you install the modules that you want, and then your code can be very similar to what you use on Colab, on Streamlit, or locally, as long as you follow good practices. We have an example where we show a complete project that goes all the way from Colab to Streamlit to then how will be a realistic deployment example, and how people are deploying this in the industry using the type of packages that people are using in the industry, like using a Celery job queue, in which you have a bunch of workers that will be solving optimization problems. And you can have, for instance, workers running open source solvers, solving easier problems, some other workers using commercial solvers, solving harder problems. And you can do this kind of mix so that in case you have thousands of instances to solve, you can manage to reduce your costs by using different solvers for different problem sizes. And since you are developing software to deploy, you want to do tests. So for continuous integration, it's just like any other Python package. So you just install it and you can run tests anywhere on continuous integration system, just like regular Python software. In terms of licenses, there are dynamic licenses. So on all these systems, you can use our licenses. That is essentially a license ID that you get, and it will just record what you are doing with it. So if you pay for 10 machines, this system will be recording what you are doing. And as long as you are within the limits, everything is fine. Otherwise, it might be time to upgrade your license. But for developing and teaching, there is the community edition and AMPL for courses that also work this way, and you can obtain them for free. So these are the two types of licenses that you can use. So you don't need to go straight to the commercial licenses. For personal use, you can just create an account and obtain a community edition license. For courses, you can apply and you get a license that gives access to all commercial solvers. This is quite powerful and a very expensive package that nobody will buy ever. No company will put so much money to buy that package, but it's really useful for teaching and for students so that you get access to all these solvers out there and you can experiment with each of them and see what they are good at and to see the advantage and disadvantages of each. And just to finish, I'm going to leave here just some links for you to see this locally. All of this that I was showing is available online. I never left the browser, and you can access all of these and go into the example and learn more. And you can also contact us in case you have any questions and in case you need any help. And thank you.
Thank you very much, Philippe. Thank you very much, Bob. That was some great information. Now on to our Q&A. And we will try and get to all these, and any other questions we do not get to, we will work to get answers for and send them out. So without further ado, let's get the first question to Bob or Philippe. How is AMPL better than Julia jump package? Can you speak to that?
So AMPL is really designed for writing optimization problems and from the ground up. And so it is really gets you a cleaner model than you can do in any programming language. Julia jump is an example of a programming language, namely Julia, where the programming constructs have been used in a clever way to make things that look like objectives and constraints and variables and such, but you can only get so far with that. So I think that's one way in which AMPL is clearly superior to the things. The programming language based optimization packages. Jump in particular is Julia specific, so it's also in some ways less able to. I mean, it sort of commits to Julia language, whereas AMPL works with Python and a bunch of other languages, and so it has the advantage there as well. Do you have anything to add, Philippe?
No, it's essentially that. Yeah. And the fact that we also separate the modeling from the programming language is really important for then people to move. Because in my part, it was all about Python. But you can also start developing just in Python. And then at some point, you want to deploy an application to run locally, let's say to install locally on Windows in C#. Your model remains the same. That I think is one big benefit of having a modeling language that is isolated from the programming language.
Awesome. Thank you. Next question. Do you have a converter to convert a model with logic operators, for example, to the corresponding model with extra binary DV? I don't know if I read that right, but does that make sense to you, Bob?
Our interface to the solvers does that, but we don't have a converter that'll directly spit out the same AMPL model with the conversion. There is a way, though, to find out what the conversion was that was done. I don't know, Philippe, do you have?
Yeah, there are some options to generate. Right now, we don't have a visualizer, but we can generate JSON files that essentially tell us what happened from the original formulation to the final one, the type of reformulations that were applied. Right now, we don't have something to easily visualize and to see why new variables and constraints were created. That part is missing right now.
Can one input the data via spreadsheet rather than in the code itself?
I'm not sure entirely what that means. You can certainly input the data from a spreadsheet. You don't have to extract the data from the spreadsheet into some other kind of file and then read that file into AMPL. AMPL will read any XOSX file directly. Doesn't matter what spreadsheet software you're using. As long as the files are in that standard format, it will read them.
Do you have benchmarks where you compare if there is any kind of penalization in performance between a natural formulation and a more specialized one?
We don't have specific benchmarks on that. One thing that we have is that in practice, it can be really hard to do the specialized formulation like we do automatically. Because, for instance, when we do the automatic reformulations for a specific expression that you have in your model, there might be multiple ways to reformulate it. And we pick the way to reformulate that from our tests performs best. And even the very similar expressions that you might have multiple times in your model, in different places, they might need to be reformulated in different ways for it to achieve better performance. And someone doing that manually, it will be really a lot of work to reach the same model that we generate. Of course, if people really know the problem well, they can certainly go straight to the best possible formulation, but with a lot of work. Unless it is like a toy problem and you already know how to model it perfectly, in that case, our formulations will be very close. But in real models, there are really a ton of variables and constraints and expressions in various places, and it can be really hard to know the right way to reformulate in each place and the one that is going to work best. The main thing that you gain is how fast you can easily experiment, because it's essentially the time between typing a few characters and spending 2 months working on a reformulation yourself.
Another quick one. Are open source solvers size limited?
No, on Colab, they are not. And also with Community Edition, they are also not limited. So once you activate the license, you get access to the open source solvers without limits for personal use. And in AMPL for courses, you get access not just to open source, but also to the commercial ones in all these different platforms and also locally.
Great. Okay, well, I think we have a couple more questions. I think we can go. We still have some people on waiting, so that's good. I know a lot of people jump off right after one, so if we'll try and get a couple more while we're here. Does AMPL integrate with Cplex, also with MATLAB?
Yes, Cplex is one of the solvers, and you can use it. It's just option solver Cplex, and we have an API for MATLAB.
Is it possible to hide the model source code using,
Amplify,
Amplify. Thinking about delivering the model to another user. Does that make sense?
Yeah, in terms of hiding, because one thing that happens when you are in Python is that typically you also distribute it is as source. If you are going to really compile it for distribution, like to produce an executable, one thing that you can do, you can encrypt your model, and then you can have code to then decrypt the model right before loading. That is one way of hiding. AMPL internally also has functionalities for users to provide encryption for models, but the easiest way is to really include in the script an encrypted version of the model, and then just have a function call to decode it. You need to generate the executable so that you are really hiding the Python code. Otherwise, people will be able to see it anyway. And that will apply not just to AMPL, but to any other tool.
Is it possible to implement complementary optimization restrictions with Python?
AMPL has a complementarity constraint that you can use, and that can be used in the Python environment in the same way as all the other kinds of AMPL expressions.
Can you comment on the installation of AMPL in HPC?
Yeah, for that, we have time-limited bundles for people in academia. That is the recommended way, especially if they are quite big. It is recommended to use time-limited bundles.
This kind of follows on to another question, I believe, because it sounds a little bit without context, but see if it makes sense. I see row diagonally, and I see row, diag, and rdiag parameters. What about column parameter constraints?
So this is likely about n-queens. So I can go back to n-queens. I can't find the question now, but essentially what we have here is right diagonal, like regular diagonal, that is this one here. And we have these diagonals here. So the two diagonals. And also they cannot be on the same column. On the same row, it is already enforced by the fact that variable row is going to indicate in which column we place the queen. So that's how we prevent. And maybe that was the question. How are we preventing them to be two on the same row? It's essential because what controls the column for each row is a variable that just has one value.
How much AMPL Python API take to create the LP file?
Yeah, so AMPL works. We have our own format to interact with the solvers, an L format, which is binary and more efficient than LP. But essentially, in terms of time, it is really hard to beat. We solve models with many millions of variables and constraints. One model that I have seen with 500 million variables. So the models can be huge, and even in the a typical model with a few millions, it takes seconds to write the NL file. We don't use LPs because LPs, they are a lot more verbose and bigger, so not as efficient. Anything in the millions that is already big, and the typical size in the industry is seconds.
Is there any CPU time difference in the if the model is implemented in Python, C, or Julia? Python's known to be a little slower at NP hard problems. Is there any computational study done at AMPL?
So in terms of performance, you don't need to worry about that when you are using AMPL, because in Python, you are just sending the data to AMPL. To send a data frame with, for instance, 1 million rows, it takes around 1-2 seconds on a laptop. And that sends the data to AMPL, and then AMPL takes care of instantiating the model. And AMPL is prepared to instantiate huge models, and that's where it is really used in the industry and is heavily optimized for that. What typical people complain about when they are modeling in Python is that you are writing Python code to generate your model. And when you are writing Python code to generate your model, it is slow. With AMPL, that is not an issue because AMPL is just made for instantiating huge optimization models. And from Python, we are just sending data in and retrieving data. It is really incomparable in terms of performance difference.
Well, that's great. I think we have exhausted our time today. Really appreciate everyone sticking on the extra time. Thank you all for joining us today on behalf of AMPL Optimization, Philippe, Bob, and all of us at Informs. Thanks for joining us. And a recording of this webinar will be available on our YouTube channel very soon. And I want to wish everyone a happy holiday and come back here next year for more webinars from Informs. Thank you very much and have a great day.
Thank you.
Thanks, everyone.